Alright everyone, we have reached our final chapter of the course. We're going to be talking about integration by substitution, and in particular we're going to be talking about two techniques that can be used to integrate composite functions. So we have spoken about how the definite integral and the indefinite integral are the inverse operations of the derivative, and we have seen that the antiderivative of the sum of two functions is as we expect, is the integral of each function independently. Now, when we were taking derivatives, we saw that when we took the derivative of composite functions, meaning a function that's made up of two functions, we had to use the chain rule. And because, as we mentioned, the antiderivative and the integral is the opposite of operation to integration, to differentiation, the issue arises of when we take antiderivative of composite functions, we have to undo the chain rule. So again, we will have two techniques of solving integrals of composite functions. One of these techniques is pattern recognition. For pattern recognition, you perform the techniques of the substitution mentally. So with this technique, the substitution is done mentally, and with the U substitution or the change in variable, you write the substitution in steps. So with the change of variables, with this technique, the substitution is done in steps. Alright, so now again, when you took the derivative of a function given by the following, so when we took the derivative of a function given by y equals f of u, and u was equal to some other function g of x, then by the chain rule we have the following, and I should emphasize this is capital F. So we have the following: we have the derivative with respect to x of f of g of x, meaning the composition of g of f with g. This was equal to the derivative of f evaluated at g of x times the derivative of g of x. So this is what we had from the chain rule. Now, from the definition of the antiderivative, we have that the indefinite integral of f prime of g of x times g prime of x dx, meaning this piece has to be equal to this piece on the inside. It has to be equal to f evaluated at g of x plus some constant of integration by definition. Remember, the definition of the derivative was, if you're given f of x dx, and that was equal to the antiderivative of f plus c. So the antiderivative of f, where an f is f evaluated of g of x. Okay, so these results that I have up here are summarized by the following theorem. And this theorem is called the anti-differentiation of composite functions. And it states the following. Let g be a function whose range is an interval I, and let f be a function that is continuous on I. So f is continuous on the function, and g is the range of the function on the interval. So if g is a differentiable function, remember what differential meant, if g is differentiable on its domain, and f is an antiderivative of f on I, then the following is true. Notice this is a lowercase f, this is a uppercase f. And the following is true. Then the antiderivative of f of g of x times g prime of x dx is equal to f of g of x, this is a capital F, this is the antiderivative, plus c. So this is the original function, and this capital F is the antiderivative. Now if you let u, this variable u, be equal to g of x, then this gives us the following. It gives us du being equal to g prime of x dx, and then we could rewrite this integral on top using our substitutions. Instead of g of x, I'm going to write u, and instead of g prime of x dx, I am going to write du. So what I'm left with is f of u du being equal to the antiderivative of u plus c. And we'll see what this means shortly. Now, let's dissect this a little bit, this formula right here. So, let us do some dissecting. So what do we have here? We have the integral of f of g of x times g prime of x dx is equal to the antiderivative evaluated at g of x plus c. So here the f function on the here is the outside function. The g of x is our inside function, and g prime of x is the derivative of our inside function. And it's important that we understand this distinction, because when we do problems where we have to take the antiderivative, this is going to come up a lot. Okay? So just remember what it meant to do a composition. If you do f composed with g, this is the outside function, this is the inside function. Inside function. So we do the inner and then we do the outer. That's how we do compositions. Okay, so let's say somebody told us to find the following antiderivative. So find the antiderivative for x squared plus 1 squared times 2x dx. Well, first of all, we have to identify what our outer and inner functions are. So first, find f of x and then g of x. So we have to identify what the outer function is and what the inner function is. Now, here we have two functions. We have x squared. Why x squared? Because this is a parenthesis being squared. So we have f of x is the outer function, it's being squared. And the inner function, g of x, is on the inside, so that's x squared plus 1. This is something that in pre-calculus, there's a lot of emphasis put in on identifying composition of functions. So I expect that you know how to do this. Now that we have g of x and f of x from this definition, we only need to find what g prime is. If we could find out g prime, if g prime is in our function, then our integral is just simply going to be f of g of x plus c. Well, what is the derivative of g prime of x? Well, the derivative of x squared is 2x. The derivative of 1 is 0, so g prime of x is just 2x. But notice, this is actually in our problem. So this is of the form, so our problem is of the form integral of f of g of x times g prime of x dx, which means that we can apply the theorem. The theorem says that if you give the antiderivative, which in this case is x squared plus 1 squared times 2x dx, then that's going to be equal to the antiderivative. Notice that I'm putting emphasis, the antiderivative of f evaluated at g plus c. What was f? F was x squared. That's what we said was x squared. I'm going to do this on the side. So side work. What is the antiderivative of x squared? That means what is this? What is the antiderivative of x squared? It's going to be x cubed over 3. So that means that this whole integral is equal to x cubed over 3 plus c. But what is the inner function? Because remember, it's evaluated at g by the definition. It's the antiderivative evaluated at g. So g is going to take place for x plus c. But we know what g is because I just defined it up here. So it's going to be equal to x squared plus 1. That's my g. But because of my function f, I have to cube it and divide it by 3 and add a constant c of integration. So I found out that the antiderivative for this problem is equal to x squared plus 1 cubed divided by 3 by using the pattern recognition method. Okay. Let's do another one. Okay, so let's say somebody came up to you and told you to find the following. 5e to the 5x dx is what you were asked to find. So here you have to be, again, a little careful. You have to know what the outer function, the inner function are. Well, the outer function here is going to be e to the x. F of x is equal to e to the x. Again, if you don't understand what's going on here, I suggest that you go back and look at your pre-calculus notes. That means that g of x is going to be the other function. The other function is 5x. And by the pattern recognition method, I need to find the derivative of g, and if it's there, then I can use it, but the derivative of 5x is just 5. So notice that I have a 5 here. Technically, I should be writing 5x dx. I should get into the habit now of actually writing the dx. But anyway, if we rewrite this, we have 5 e to the 5x times e dx. This is our f of x, this is our g of x, and this is our g prime of x. So this fits the definition of the rule that we had, and I'm going to rewrite the rule again. So I'm going to rewrite it again for your convenience. So we have, if you're given f of g of x times g prime of x dx, and this is equal to the antiderivative evaluated at g plus c. Okay, so what is the antiderivative of f? So I have to find out what the antiderivative of e to the x dx is. But we know from way before that this is equal to simply e to the x. Okay, so what do I have? I have that this is equal to the antiderivative of f, which is e to the x, evaluated at g of x, but g of x is 5x plus c, and that's my solution. Again, I'm doing what I did here. I did f evaluated at g of x plus c. F was e to the x, so it's evaluated at g of x, which is e to the 5x plus c. If you take the derivative of this, you'll get back the same problem. So let's check our work. How do we check our work? We simply take the derivative. We'll take the derivative of this. So we'll do d dx of 5x plus c is equal to the derivative of e to the 5x, right, plus the derivative of c with respect to x. We know this part is the right part is going to be equal to 0 because the derivative of a constant is 0. And then by the chain rule, the derivative of e to the 5x is e to the 5x times the derivative of the top, which is 5. So we get 5e to the 5x. But that's exactly what we began with, 5e to the 5x. So we have the correct antiderivative. Again, this is the so-called pattern recognition. So it turns out that we can use this pattern recognition technique with the constant multiple rule. So what does that mean? That means, remember the constant multiple rule said that if you have a constant times f of x dx, that was equal to the constant times the integral of f of x dx. So we can actually use this in our problems. So let's actually do a problem. Let's say, I believe this is example 3. Let's say somebody comes up to you and tells you to find the following antiderivative. So find the antiderivative of x times x squared plus 1 squared dx. Now this is very similar to the first example that we did, but instead of having a 2x, now we have a single x. So it's going to be a little bit different. Now, again, f of x was x squared. That's just the outer function, this piece. G of x is going to be the same as before, x squared plus 1. But now, notice that the derivative of g prime of x is 2x. But I don't have a 2x here. I only have an x. So I have a problem. I actually have a big problem if I cannot use it. So what I'm going to do is I'm going to introduce a 2 in there. Remember the rule that I gave us was the following: the antiderivative of g of x dx, well, g of x is g prime of x dx is equal to f of g of x plus c, provided that you have the derivative in there. I don't have the derivative in there because I'm missing a 2. Well, what I can do is I could add that 2 in there. How am I going to add this 2? I'm going to multiply and divide by 2 at the same time. So what do I mean by that? I'm going to divide by 2. It's the same thing as multiplying by 1/2. I'm going to multiply by 2. Notice that 2 times a half is just 1, so I'm not changing the problem. It's just the same as multiplying by 1. X times x squared plus 1 squared dx. So these two things are equal, these two integrals. Now what I can do is, using the constant multiple rule, I'm going to factor out that 1/2. I'm going to take it to the outside. And now I have 2 times x, it's just 2x, times x squared plus 1 squared dx. And notice that now I do have g prime in there. I do have g prime of x in there. And I do have f of g of x in there. So I can actually apply the theorem. So that means that I'm going to have 1/2, which is on the outside, times the antiderivative of this. Well, the antiderivative is going to be, again, x cubed over 3, because, again, the antiderivative of x squared dx is equal to x cubed over 3 plus c. So it's going to be equal to x squared plus 1 cubed over 3 plus c, much like we had in the previous problem, which is equal to, when you multiply, x squared plus 1 cubed over 6, because 2 times 3 is 6, plus c. Remember that when you multiply a half by a constant, it's just going to be a constant, so we just leave it as is. And this is our solution. So this technique that I did here, I introduce a constant. I introduce a constant into the problem. Now, typically when you do this type of problems, you will not actually do this many steps like I did, but for the purposes of actually showing you the problem, you'll do it in that many steps. Now, there's something important, and you need to take note. The constant multiple rule, which allowed me to multiply by 2 and add and divide by 2 at the same time, multiple rule applies only to constants. You cannot multiply and divide. A lot of students get this wrong on problems. Divide by a variable and move the variable outside the integral sign. Just can't do that. For example, you can't do this. You cannot do like x squared plus 1 squared dx. It's not the same thing as 1 over 2x times the integral of x squared plus 1 to the 2x dx. What I did here was, I cannot take the antiderivative of this, because if you notice here, f of x is still x squared, g of x is still x squared plus 1, but now g prime of x is 2x, but I don't have a 2x at all in here. Notice there's no 2x. So what did I try to do? I tried to introduce it by multiplying and dividing by 2x. This is not allowed. So, not allowed. So be careful. A lot of students make that mistake, and it's a fatal mistake. It's a very fatal mistake. So I'm going to end this part here, and when we come back, we're going to talk about the next technique, which is called the change of variables technique.